So, okay, so I'll give you the final answer. That is 97.555746. So it is like something this times 93.0 plus this times 96.2 plus 100 plus 104.2 plus 108.7. Okay, last point will be this one. Okay, you can also check how you can solve these using the calculators. Okay, so why less number of people? If it is, we are counting all your session as a attendance, so you have to participate in all your all the session. Okay, okay, that's that. Okay, so that's all about our I mean chapter number 3, but we also have one heading, but I'm not gonna teach you in here because of time consumptions, and you can, but it is your reference that I also mentioned in your module as your reference. Okay, so something I am giving you as a reference for yourselves. Okay, so since because these questions also arrived in past papers, so this is all yours. Okay, so you can try to understand this concept using any mode of internet, or so many ways or books. Okay, this is your homework reference, so you can refer these things. Okay, it's not the big thing. Okay, only thing, so you have to find the errors. Okay, so the from the value to whatever the approximations. Okay, that is exact values should be this one minus this one. So we already studied everything about the errors in our chapter number 1, so you can refer that one. Also you can refer this point of notes and just understand it. Okay, that's all about this one, chapter number 3. So for time being, I'll start what's the time now? Yeah, so we have one more session, so I can use to start our chapter number 4. Okay, but I'm not fully typed or fully used it, but anyhow, I'll start it. Okay, yeah, give me a second. Please, in the meantime, can you finish up that question? I will come back quickly. Okay. So let's begin. Can you see my screens?
Yes, ma'am.
Yes. Okay. So this is we have almost finished our course. We have 1 or 2 weeks. Okay. So hopefully I will try to finish chapter number 4 as well as I will prepare your continuous assessment as well. Okay. So in the meantime, you also prepare yourself to answer all the finished chapters and the rest of the chapter. I will today is our 10th lecture, so 11th, 12th. So hopefully we'll finish chapter 4. Yeah. So this is all about our chapter number 4. It's numerical methods of solving differential equations. Okay. So far we have seen, how to use our numerical analysis to solve, kind of algebraic equations. Okay. Now we are trying to solve these of our differential equations. So since you are with the differential equation courses. Hope it will be somewhat, So in that ODE, you are studying about how you can solve the differential equations in analytical way. It means exact equation or analytical solutions. We use that terms word, okay? Here we are using our numerical way to solve the same differential equations, okay? So here we can use Euler's method or linear multi-step method or Taylor method or Runge-Kutta methods, okay? So I will try to cover up all these methods, okay? So each methods are countable because in the exam also, they may choose any method for you to, find the answer. They won't ask you to, solve yourself. They will ask you to use the Runge-Kutta method or Taylor method or Euler method, something like that. So you have to be familiar with all the methods possibly, okay? So yeah. So let me, this is the interaction part of chapter 4. Since I'm not typed yet. So in the meantime, if I type, I will send you the notes. But for the time being, you have to use my written answer, written notes here, but don't expect me to, type and send all the notes, okay? So I'm using some techniques to write here, so you have to follow me. Don't wait for me, my notes. If I got time only, I will send you. Otherwise, this is all your notes, okay? So chapter number 4, it's about solving the numerical solution of differential equation, okay? Numerical solution of differential equation, not a difference, differential, yeah. Okay, give me a second. Differential equations. Okay, so let's first of all begin with a single step. Okay, so the heading goes, the first one goes single step method. Okay, so single step method, it's like from one, we have done earlier, like P1 to P2, we have gone to P2. Okay, P3, something like one step away. Okay, so we can see what it is first of all. So please write down these notes for some time. So suppose a first order. So we are trying to solve mostly first order here. Okay. Yeah. First order differential. Please write down fully. I'm just using these abbreviations. So differential equation with initial conditions. So how comes to solve a first order differential equation with initial condition? Okay, is given by so as we know how we can notate our first order differential equation, dy over dx, which is equal to f of xy with some initial condition. For example, y of x naught will be y naught. Okay, let's say this is my equation number 1. All right. Okay, let's continue. Please write with me, so it's better for me to, when I'm using the new window, it will be helpful. Okay. Next one. So let again y of x1. Let's say we know y of x naught already in the initial conditions. So let y x naught, okay, is the approximate solution of equation number 1. Okay, let's say. So since dy over dx, okay, of something f of xy, okay, so what do we need to do, what we are going to solve? Actually, we want to find the solution in terms of y, no, isn't it? So the function of the y will be in the function of x comma y. Okay, so sorry, y will be a function of x. Okay, so actually our thing is what we are going to do is we are going to solve y, okay, from these equations. So we have given our first at the x naught, what is it? Y naught is given, okay, as an initial condition. Okay, so next point is we have to find the y of x1. Okay, so y of x1 is the approximate solution of equation number 1 for, okay, tell me what is x1 actually. X1 is in the sense, so we have taken from the x naught, we will take one step away, isn't it? 1h. Okay, x naught will be x naught h. For example, if I draw this one, so this is my x term, this is my y. Okay, y of function of x. For example, let's say my function will be f of x, something like that. Okay, so this is my, let's say, x naught. Okay, so this will be my y naught. Okay, this is my initial point they have given. Okay, so there's nothing here. So this is my initial graph. Okay, and then I'm gonna find y x1 point. Okay, this should be something here. So this will be this x1 will be x naught plus h. Okay, we are taking equal length. Okay, equal differences. So to find this y1, okay, y1, that can be seen as y of x naught. So this will be y of x naught. This will be my y of x1. Okay. So for this one, we are going to use the single step method, which called as a it has been derived from the Taylor series expansion. Okay. So this is our purpose. That's what they say. Let yx1 is the approximate solution of the equation 1 for this point. Okay. Now using Taylor series. Okay. Taylor is a mathematician who has given so many things. Also, we have studied in our chapter number 2, I guess, in Taylor polynomials. Okay, like this, he also given one more results of Taylor series. Okay, we call Taylor series expansion. Okay, sorry about this. This will be y. Okay, Taylor series expansion. Okay, so I don't know, you may heard this expansion, so I will write it. Okay, if you wanted to find the Taylor series, actually is we are finding the value at the point. Okay, let's say if you wanted to find in this x1, this will be equal to y of, okay, y of, actually what is x1? X naught plus h no. So we can write this equation in the Taylor series as, first of all, y of x naught. So I have, we have seen this one so many ways, but this is that forward, Newton forward and backward and everything has been derived by this series. Okay, now only we are studying that one. Okay, the next term will be h time y dash of x naught. So be careful. So it is like a delta y naught, kind of things. Okay, in here, there we have used delta y naught. Here, first of all, you write this point. Okay, then h time this term's first derivative. Okay, again, so it is like a 1 factorial. So you don't need to write. Okay, h squared divided by 2 factorial against second derivative of x naught. Okay, so it continues. Next one will be third, fourth, fifth. It goes. Okay, so until the last point. Okay, last point I can write like h to the power. Okay, yeah, I can write like this. H to the power, let's say kth point. Okay, OHN. So I'm just avoiding to write the n because of purposes. Okay, h to the power k of k factorial time. What do you think? This will be y of, we used to write this one for the derivative, nth derivative of x naught. Okay. Okay, still we are not finished. Okay, this is our kth term. Okay. Give me a second. I can write nicely. So this is my, it's like a I term. Okay, I'm using kth term. Okay. Again, it's continuous. So it is going up to the infinity. Okay. So therefore, we are writing up to the, kth term, and then we are writing the error terms. Okay. Because since we are approximating, isn't it? So it is going up to the infinity level. Okay. It is going more and more nth. Okay. So we are writing up to the kth point, and we are writing all the other terms as the error terms. Okay. Like a common term as h of, okay, please write down k plus 1 divided by k plus 1 factorial times y to the power k plus 1 derivative of x naught. Okay, here don't use x naught, we are using f, sorry. First of all, I need to write nicely. So this is our h. Okay, so this is our y to the power k plus 1 derivative of, rather than x naught, I'm using psi naught or epsilon naught. Okay, I will tell you what it is. Okay, where, okay, where, write down. So this is actually our Taylor series. Okay, so where this epsilon naught, okay, oh, you can write like this, like epsilon. Okay, no need to write the psi. Just a second. This will be epsilon. Okay, k plus 1 epsilon, which is called as which has between, so epsilon between the x naught and x1. Okay, since we are finding our next step, so I said you this is kind of a single step, one step process. So we know x naught terms. Okay, so if you wanted to find in the x1 term, we are using x naught terms for our calculations. Okay, derivatives. So the error point, okay, in the error point, if you have epsilon, this epsilon, we are not taking x naught. Why? Since we are writing commonly, no, so that's why I'm writing epsilon. This epsilon belongs to x naught, and because in this period only, in this here only we have the epsilon somewhere. Okay, that's what it means. Okay, can you write correctly? So if you need it, I'll write again. So actually our Taylor series is x naught is y of x naught plus h. So rather than, so x1. So rather than here to write this one, you better write this one. Okay, so it will be easy for you to remember. So first of all, I need to write my x naught term plus h time y dash of x naught. Okay, it's like a 1 factorial. Again, h squared over 2 factorial of y double dash of x naught. Okay, what about third one? h3 over 3 factorial y triple dash. Okay, so third derivative. So it goes up to n, let's say kth term. Okay, so since if you write n term, it will be like this, no? So to avoid only, they are using some k's. Okay, so it's not a big problem here. So k derivative of x naught. So since we are using y of k as a power, okay, so better you use in a bracket as a derivative. Okay, and then one more extra term, it is error term, which called as a xk plus 1 divided by k plus 1 factorial of y of k plus 1 derivative of, here we are only using epsilon. Okay, let's write down nicely. Okay, so epsilon also belongs to x naught comma x1. Okay, all right. Now since so next point. Okay, since dy over dx is equal to f of x comma y, and then a y dash of y, give me a second. Okay, y dash x naught, which is equal to what? So I can put y f of, okay, x naught, okay, then y of x naught, which is equal to f of, sorry, it's not a dash. Okay, so dy or dx equal to f of x comma y. So y initial point, which can, transfer y is equal to fx comma y now. So I can put f of x naught and this term also y x naught. Okay, there we can put as a y naught. Okay. Yeah, give me a second. I think, sorry, this should be, yeah, why I'm writing this. Okay, give me a second. There's a typo error, that's what I'm struggling. Okay. It should be y dash. Why? Can anyone tell why it should be y dash? Then the y x naught. Anyone answer me? Is that y x naught or y dash x naught? Which is possible? Denoting y of x naught by y naught. Okay. So I also allocated some people for attendance. They didn't answer me. So still I didn't put you the attendance. Okay. So okay. So is that y x naught or y dash x naught? What do you think? Why I'm choosing y dash? Because see, what is dy over dx? Dy over dx is the y dash now. Okay. So it means this is fx comma y. Okay, so if you put y dash of x naught, it should be whatever the f of x naught comma y x naught. Okay, so that's what it means. So it should be y dash. Okay, so denoting y x naught is equal to y naught. Okay. Okay, let me continue. Further differentiating dy over dx is equal to f of x comma y. The values of y dash x naught, y double dash x naught, up to y of k of x naught can be, because we have to, sorry, in the Taylor series equation, please put as the equation number 1. Okay. I think 2. Sorry, it's 2. Okay. Because I have taken 1 already, this equation. Okay. So, yeah, this can be further differentiating values of y dash, y double dash, y of k x naught can be computed. Okay. Okay. So actually what it says is to find the y of x, x1, we have the Taylor series. Okay. The Taylor series needs these values. Okay. So this value can be obtained from here. Okay. So this also you can write as a y dash. Okay. So that's optional. Just for the, we're going to use it later. Is equal to y dash. Okay, so let me continue. Substituting these values in equation number 2, okay, and leaving the error term, we have what we have, y of x naught, x1, which is equal to y of x naught plus only the other term, no, y dash of x naught, x squared over 2 factorial of y double dash x naught up to the kth point. Okay, so hk over k factorial times y of k x1. Okay. Okay. So this I can write in a simpler way. This is my y naught. Yeah, this I can write as my y1, which is equal to y naught plus h, okay, y dash h naught plus h squared by 2 factorial y double dash x naught, okay, up to, for this one I can write xk over k factorial times, yeah, y to the power k rho, sorry, yeah, this one should be y naught, okay, don't write this, y naught, this one y naught, okay. So I'm just writing in a simpler way. So y naught plus 2 factorial y naught double dash, okay. So it continues. Okay, so we have 10 minutes. Let me finish up this stuff. Okay, let me continue. Okay, suppose the values of y are to be computed at x2, x3 up to xn in continuation of x1. Okay, from the x1, after the y value of x1 we have find from the, from the y naught value. Okay, then we can use this value to find x2, then x3, up to every steps we can go. Okay, so then compute the values using the value of y at preceding point. Preceding point means the next point, okay? Next increasing point. Point step by step. Okay, so step by step we are finding. So therefore, this type is called single step method or one step method. Okay, so one step method or single step method. Okay, so if I ask you, let's say in the questions, describe or briefly describe what is the meaning of single step method. Okay, so you have to write this point. Okay, so from each point to we are finding the preceding point. Therefore, it is we called as a single step or one step method. Okay. Okay, so let me continue. Okay, continuing. So from the equation number 2, we can abbreviate the full big, equation as in this way. yi plus 1. That means the next step of yi can be computed by yi plus h time. Let's take tk plus tk minus 1, something. Okay, we are denoting, okay, tk minus 1 of point xi comma yi. Okay, so it means at the ith point, okay, I plus 1 point, we have to use the ith point value plus h times something tk plus 1. So let's define what is that. Okay, so I think it should be, yeah. So where tk plus, so tk minus 1, x naught, y naught, we can, so xi. Okay, so I term which is equal to f of I plus h. So we are, writing everything as a t. Okay, so f of, fi dash plus h squared by 3 factorial fi double dash. Okay, it goes up to kth point. Okay, if it is k minus 1, so you have to go up to k minus 1 point. Okay, k factorial fi k minus 1. So why I need to go up to k minus 1 term? So since we are starting from 0, here we can say something, there's nothing, no? So it goes up to k point, okay? So that's why, so I hope you are copying, okay? So in the, go through the equation number 2. So it has, it is going up to hk. So, yeah. So we also have the k plus 1 term we are taking as the error. Okay. So for the I can take the values of 0, 1, 2, up to n minus 1. Okay. So one step less. Okay. tk minus 1, we are going up to tk minus 1. Here we are using okay. Did you understand this, why it is coming as? Okay, I will easily explain it. See here, I have taken 1h here. So actually, in the equation number 2, I'll go back to the equation number 2 again. Okay. Yeah. So this is our equation number 2. Okay. Okay, let's take another color so it will be easy for you to understand. Okay, see here, this is our equation number 2. Okay, y1 is go y naught, h square to y naught double dash. Okay, so we are taking up to here. This is the error term we are omitting. Okay, for some time. So it is there in our equation number 2, but for our purposes, we are omitting this term. Okay, we are only taking up to yi. Okay, this term plus for up to these terms. Okay, yeah, sorry. Yeah. So up to this point, I'm taking as a tk minus 1. Okay, with h also. Here, see the last point only. Okay, I will take there. Okay, our last term will be, actually our last term will be h to the power k over k factorial time something f to the power k and x naught something. Okay, so here they have taken h extra h. Okay, so it is like we are multiplying by h. Okay, this is something like this, no? Yi plus h time fi plus h by 2 fi dash. If I put like this, hk minus 1 over k factorial fi k minus 1. See, again take the h inside, so h of fi, h squared by 2, h cubed by. So if you multiply this term, what you'll get? You'll get h to the power h into h k minus 1. So it is like a same, base, you have to add. So k 1 plus k minus 1 will be k. So we will reach, isn't it? So what they are doing is they are taking one h outside. Okay, all the rest of the thing only they are writing. So that's the idea. Okay, hope you understood. Okay, so please write down. Continue this things. So this is known as Taylor series method of order k. Okay, I think I'm run out of time, so I'm just finishing here. Okay, we'll continue in the next lecture. Okay, thank you.